Hi, everyone. So now we're going to start talking about our salts. And I wanted to start off by giving you a definition for what a salt is. So a salt is a compound that is produced when the hydrogen ion from the acid is replaced by a metal ion or by the ammonium ion. That is the definition of a salt. So for example, if I had hydrochloric acid here, right, and I replaced the hydrogen, then I am going to form chloride salts, right? So because the chloride portion will stay, but there will be a metal that replaces it, right? So if I'm using hydrochloric acid as my acid, and I react it with either a metal or a base or a carbonate, yes, the hydrogen will be replaced, but the chloride will stay and my salt will be a chloride, right? For example, I could replace the hydrogen with sodium and I would end up forming sodium chloride as my salt. Now, if I'm using sulfuric acid as my acid, then I expect to form salts which are sulfates, right? So I would form sulfate salts. For example, if I replace the hydrogens with calcium, I could get calcium sulfate, which is a salt. If you are using nitric acid as your acid, then you expect to form nitrate salts. So had I replaced the hydrogen there, say for example, I replaced that hydrogen with aluminum, then I would have had aluminum nitrate as my salt. Okay, so these are the top acids that we usually use when we are making salts. But just remember, once we replace the hydrogen ion with a metal, we would have created a salt. Okay, it doesn't have to be a metal. We could also replace it with ammonium, the ammonium ion as well. So for example, we could have a salt with the ammonium ion. For example, we could have ammonium chloride. We could also have ammonium sulfate. Okay, so we could have replaced the hydrogen ion with the ammonium ion, and that would have still allowed us to form a salt. Okay, I should also remind you of another acid. Remember, this is phosphoric acid. So if I use phosphoric acid, I'm expecting to form phosphate salts. And less commonly, we do have weak acids as well. For example, ethanoic acid. If I use ethanoic acid, remember I replace that hydrogen that's beside my oxygens, and I would form ethanoate salts. Okay, and this one is a little bit unusual because usually we would put the metal first and then the non-metal anion or the anion next. But in this situation, we normally put the negative ion, which is the ethanoate ion first, and then we put the metal after. So this would be an example of sodium ethanoate, which will be formed from ethanoic acid. So again, let's continue our discussion as to what are salts. So a salt is a compound which is ionic because it is made up of non-metal and metal ions. So the salt is ionic. It has positive ions, it has negative ions. So for example, if we have sodium ions reacting or combining chloride ions, we would get sodium chloride. If lithium combines with bromide ions, we get lithium bromide. Magnesium reacts with sulfide ions, we get magnesium sulfide. Calcium and oxygen gives us calcium oxide. Iron 2 plus and Fe fluoride ions give us iron 3 fluoride. Now remember, when you see numbers when you see Roman numerals beside a metal, it is there to tell you the charge of that metal. So it is saying to you that this is a transition metal and it can have different charges. So for you to know which charge you are to use, it's normally put in Roman numerals beside it. So let us now look at what are the properties of our salts. So let's go. Most of our salts are soluble in water, but not all right? So I don't want you to think that all salts are soluble. And in fact, we are going to have to go through the solubility table so we know which salts are soluble. Salts are able, when they are in water, they act as good conductors of electricity because they will produce mobile ions when they are dissolved in water. Some salts are white crystals, whereas some are colored. For example, copper sulfate is blue. Ferrous sulfate, which is iron 2 sulfate, is green. Some salts contain water molecules trapped inside them, and this is referred to as the water of crystallization. The salts that contain water of crystallization are referred to as hydrated salts. For example, copper sulfate, the crystal of copper sulfate actually does have water in it, all right? So for you to make the crystals of copper sulfate, you must have 5 water molecules as well. So these water molecules here are known as water of hydration, right? Water molecules of hydration, which are helping to make the crystal of the salt. Now let's look at uses of salts. So they have various uses. For example, sodium chloride, which is a common salt, is used for seasoning, preserving food, and it's essential for most life processes. Sodium carbonate is also known as washing soda, is used as a detergent. Sodium bicarbonate, also known as baking soda, is used in baking powder and in the manufacture of glass and in fire extinguishers. There's also potassium nitrate, also called nitro, which is used in fireworks and is the main, it's used in the manufacture of fertilizers. Sodium nitrate, which is called chili saltpeter, is used as a fertilizer and in the manufacture of gunpowder. Calcium carbonate, also known as limestone, is used in constructions of in the construction industry for buildings and in the purification of iron in the blast furnace. Calcium sulfate is used, also known as the plaster of Paris. It's used in the cement industry and in the synthesis of sulfuric acid. It's also used to make the casts for persons who have fractured a limb, and you see them walking around with a cast. Is usually made from calcium sulfate. Calcium phosphate is a bone mineral, but it's also used in the manufacture of fertilizers and in medicine. We have potassium aluminum sulfate, also known as alum. It's used in water purification and the textile industry. Ammonium chloride is used in soldering and in dry cells, and copper sulfate is used as a fungicide and in the textile industry. So from time to time, you will be asked about the uses of salts, which is why I went through this. Now, one of the main things you have to know about salt, apart from being able to write the formula of the salt, is to know whether or not it's going to be soluble in water, yes or no. So you have to memorize the solubility table. You have to memorize it, because when we look at how to prepare our salts, the preparation of our salt depends on whether it is soluble or not. So we're going to go through this table, and you have to find some way to memorize the solubility table. All right, so let's look at the soluble salts, or the soluble compounds, or soluble ionic compounds, right? So firstly, any compound that has a group 1 metal in it is soluble. So once a compound has lithium, sodium, potassium, etc., or if it has ammonium in it, you don't have to wonder, that compound is soluble, okay? The second thing is that nitrates. If the compound has the nitrate ion in it, it is soluble. If the compound has the acetate ion in it, it is soluble, right? So, and you don't really need to know much about the perchlorates, so I'll just erase that one. All right, so nitrates and acetates are soluble. So you don't have to question when you see a nitrate ion if the substance is able to dissolve. The next one to look at now is, what about when you have chlorides, bromides, and iodides? Now, most of these compounds are soluble. So most compounds that have chloride, bromide, and iodide are going to be water soluble, except for when you have these metal ions bonded to your chloride, your bromide, or your iodide. So if you have silver chloride, so let me put them over here. So these are the ones which are insoluble. If you had silver chloride, that's insoluble. If you had silver bromide, that is insoluble. And if you had silver iodide, that is insoluble. So we're saying if you have silver bonded with any of these halide ions, it is going to be insoluble. The same situation is there for lead. If you have lead chloride, it is insoluble. If you have lead bromide, it is insoluble. And if you have lead iodide, it is insoluble. right? The same thing goes for copper and mercury, right? But the main two you must remember are that these give us insoluble halides when they are bonded to the halides. Now, the next one would be the sulfates. These are the ones that have the sulfate ions. Now, most sulfates do dissolve in water. Most of them are soluble, except for a few sulfates which are insoluble. So if you have calcium sulfate, that is going to be insoluble, it doesn't dissolve. If you have strontium sulfate, it is insoluble. If you have barium sulfate, it is insoluble. And also if you have silver sulfate, right, and lead sulfate. So these are the ones which are the exceptions to the rule, but if you don't have any of these, then the sulfate is soluble. Let's look at the others now, these other two, which the majority of the compounds are insoluble and only a few are soluble. Now, hydroxides. Now, most hydroxides fall underneath the insoluble category, also most sulfides as well. They are insoluble. But the exceptions would be if your hydroxide contains a group 1 metal, like lithium, sodium, potassium, ammonium. Also, if you have calcium, strontium, or barium. If you have these are the exceptions to the rule. They usually will dissolve, whereas the rest of them would be insoluble. I shouldn't let you know that calcium hydroxide is partially soluble, right? So it's kind of, it shouldn't be considered as being fully soluble, it's partially soluble. And also we have our carbonates and our phosphates. If you have the carbonate ion, there is a high chance that you are not soluble. And if you have the phosphate ion, the high possibilities that you are not soluble. The only carbonates and phosphates which are able to dissolve in water are the ones which contain group 1 metals like lithium, sodium, potassium, ammonium. So if you had sodium carbonate, that would be soluble. If you had potassium carbonate, that would be soluble. And the same thing goes for the phosphates, right? But any other phosphate would be deemed insoluble. All right, so now we're going to see if we can practice what we've just done in terms of salt solubility. So what we're going to do is that we are going to be writing the formulae of these salts, and we are going to indicate if we think it is soluble or not. So starting off with sodium nitrate, I'm actually going to just show you how to work out the formula of the salt just as well, just so you can remember. So sodium nitrate would have the sodium ion and the nitrate ion, and luckily they both have the same charge. So therefore, the formula of that salt would be NaNO3. Now, should it be soluble or insoluble? It is soluble because remember, all nitrates are soluble. That's one reason. Plus also, all sodium salts are soluble. So this salt is soluble for two reasons, because it has the nitrate ion in it and it has sodium ions in it. So it's soluble, okay? Next, what about aluminum sulfate? Okay, let's work out the formulas. Aluminum has a 3+ charge because it is in group 3, and the sulfate ion has a 2- charge. So these charges are not the same, so we have to cross multiply the charges. So the 2 that was beside the sulfate comes beside the aluminum, and the 3 that was beside the aluminum goes beside the sulfate. But we have to put the sulfate in brackets because it is a polyatomic ion made up of more than one elements joined together. So here is our aluminum sulfate. So then we would think back on our rule about sulfates, and it did say that all sulfates or most sulfates are soluble except for lead and barium sulfate. So aluminum doesn't fall in that exception. Aluminum sulfate is soluble because it's not lead or barium sulfate. Okay, let's look at this other one here. This is lead bromide. Lead has a charge of 2+. The bromide ion is -1. These numbers are unequal, so we must cross multiply. So the lead ends up getting the 1 that the bromine has, but we don't put the 1, we assume it's there, and the bromine gets the 2 that was beside the lead. So this is the formula of lead bromide. Now this one is going to fall into the insoluble category because we did say that most chlorides or most bromides are soluble except when you have lead or silver bromide. So this is lead bromide, so it is insoluble. Finally, we have potassium carbonate. Potassium is in group 1, it has a +1 charge. The carbonate ion has a 2- charge. Numbers are unequal, so we cross multiply. So we get K2CO3. So this one falls under this soluble category because even though most carbonates are insoluble, but the fact that it has potassium in it, that's what causes it to be soluble, right? So carbonates are insoluble except for those that contain sodium, potassium, or ammonium, right? Or lithium as well. So here we have just practiced the writing of the formulae of our salts, and we have practiced their solubility because, as I said, you need to have that information to know how to make your salt. I also wanted you to know that we can classify our salts into one of two categories. We do have salts which are considered to be normal salts, and a salt is said to be normal when all of the replaceable hydrogen ions in the acid have been completely replaced by metallic ions. So for example, if you have sulfuric acid which has 2 hydrogen ions, if all 2 hydrogen ions are replaced in that acid, then you will form a salt which is normal. There are no hydrogen ions remaining in this salt. Similarly, if we react hydrochloric acid and replace the 1 hydrogen that's there, we will form a normal salt that has no hydrogens that are in it. However, we can form acid salts, and we can form acid salts if we are using dibasic or tribasic acids, which have more than 1 hydrogen ions to be replaced. Now, these acids allow us to be able to form acid salts if we wanted to do that. Okay, so if you're a monobasic acid, you cannot form an acid salt because you only have 1 hydrogen to be replaced. And once that 1 hydrogen is replaced, you will form a normal salt. But you can have acid salts from dibasic or tribasic acids. So acid salts are formed when the replaceable hydrogen ions in the acid are only partially replaced by a metal and are acidic to litmus paper. So here we have an example. If we had sulfuric acid is considered as a dibasic acid because it has 2 hydrogen ions to be replaced. If we only replaced 1 of the hydrogen ions with a metal and we allowed 1 other hydrogen ion to remain in that salt, then that salt is an acidic salt because it still contains hydrogens which can be replaced. Okay, so that's the difference between an acid salt, which still contains replaceable hydrogen ions, and a normal salt, which does not contain any replaceable hydrogen ions. So sometimes you may be asked in a question, how would you tell a normal salt apart from an acid salt? Like, for example, if you had an acid salt and a normal salt and you got them mixed up in the lab and you wanted to check which is which, and so you could relabel them, then what are the ways you could tell them apart? Well, one way is that you could test the pH. You could dissolve both of them in water and test the pH with a pH meter or with pH paper, indicator paper. A normal salt should give you a pH of 7. An acid salt is acidic, so it has a pH of less than 7. You could also use litmus paper. So you get the litmus paper, you add the salts first to water, then you put litmus paper in it. Whether you're going to put both, well, in this case for the normal salt, you're going to put both types there. So you're going to put red and blue, right? And you're going to notice that the normal salt doesn't change either of the two. But if you put blue litmus paper in the acid salt, it is going to turn it red. And that is indicating that salt is acidic. Another way you could tell them apart in the lab is that a normal salt, which has a pH of 7, will not react with a carbonate or a base. However, an acid salt, which is still acidic, is able to react with bases, and it is able to react with carbonates. And we actually prefer the reaction with the carbonates to test in the lab, because this reaction would actually give us carbon dioxide, and that would give us effervescence, and we will see fizzing. So it meant that if I had a container that has the normal salt and one that has the acid salt, if I add some carbonate to it and I look to see which one gives me bubbles, then I know that the one that gives me bubbles would be the acid salt. All right, with that being said, I want to introduce you now to how we can make salts in the laboratory. All right, so I wanted to introduce you to how you should think about what do you do to make your salts? So if I ask you to prepare a salt in the laboratory, the first thing you should ask yourself is this salt soluble in water? Yes or no? If your salt is not soluble in water, then there is one method to use to prepare an insoluble salt. It's called the precipitation method. And in that method, you will mix two solutions together that contain the positive ion that you want and the negative ion that you want to create that salt. We will go into the methods of how this is done in our next session. So if your salt is insoluble, you must use the precipitation method to prepare it. However, if your salt is soluble, you must ask yourself another question. Does the salt contain sodium, potassium, or ammonium in it? If you are preparing a salt that has sodium, potassium, or ammonium, and the answer is yes, and it is soluble, then you have to do the titration method to prepare that salt. So in the titration method, you react an acid with a solution of your alkali, which is either sodium or potassium hydroxide, or you can use the carbonate of sodium or potassium, all right, to create your salt. So salts that are soluble, which contain sodium, potassium, or ammonium, are prepared using the titration method that would react or acid with the alkali of sodium, potassium, or ammonium. Now, what if you are making a soluble salt, but it does not have sodium, potassium, or ammonium in it? For example, if you're making some calcium sulfate is soluble, but it doesn't have sodium, potassium, or ammonium. If not, then you are directed to this area here. If you are preparing a soluble salt that doesn't have sodium, potassium, or ammonium, then you use a method called the excess reagent method, which we will go into more details in when we look at the next session, right? So in this method, the excess reagent method, you prepare your salt by reacting the acid with an excess of either a metal or the metal oxide or metal hydroxide or the carbonate that you desire. So if I'm trying to make calcium sulfate, then I'm going to use the acid that has sulfate in it, which would be sulfuric acid. And then I have a choice of reacting the sulfuric acid with the calcium metal or the calcium oxide or the calcium hydroxide or the calcium carbonate. So that is what it means. So the key thing is that we do have three methods to prepare salts in our lab. We have the precipitation method for those salts which are insoluble. We have the excess reagent methods for those salts which are soluble, but they don't have sodium, potassium, or ammonium. And then we have the titration method for those salts which are soluble, but they contain sodium, potassium, or ammonium. So we will continue with our salt preparation in our next session.